The C++ standard library comprises of stream.io, strings, the standard template library or the STL, threads, and utilities. Of these, we will examine the first three, that is stream.io, strings, and the STL in this video. The next video would cover threads and utilities. So let's get started with these topics for the C++ standard library. How to use the standard library? The standard library is available under the std namespace. So to access a class or an object from the standard library, we need to use the scope resolution prefix std:, like std:"cout" or std:"string". The next thing is to include the relevant standard library header files in the program. The header files are like iostream for standard input, output, and error streams. iostream is easily the most commonly used header file. String for using the std string class, vector for the std vector container, similarly map for the std map container, unordered map for std unordered map container, and algorithm for using the std algorithms like std copy, std find, std sort, etc. There are many more header files and we'll find them as we see the example programs. The standard library provides streams for I/O. A stream is like a pipeline in which data flows. A program writes to a stream and the data might end up on the video display or a file or network. Similarly, a program reads a stream and the data might be coming from the keyboard or a file or the network. The data flowing in the stream can be of characters or it can be binary data. Let's look at the two cases separately. And first, the character-based stream.io. And characters here follow a format. It's like we have a format, character string followed by an integer and the double precision floating point number. Now we say integer, double, etc. But these are characters, not the binary representation. Say an integer like 123, which we write as characters 1, 2, and 3. So kind of we had an integer like int I, which had a value 123 and we printed as character 1, 2, 3, or we read it as characters 1, 2, and 3. std::stream is a class for output streams, and there are two important global objects of this class, and these are std::cout for standard output, which by default is connected to the video monitor screen, and std::cerr is another object of class std::stream, and it is the standard error stream. It is also connected by default to the video monitor screen. In Linux environments, these streams correspond to file descriptors 1 and 2. Then we have the put2 operator, which writes the second argument on the first. So if we say std::cout <> hello world, it writes hello world on the standard output stream, and you can see it on the video monitor screen. Similarly, you can write std::cout <<i or std::cout <d or std::cout <c, and all these values appear on the screen. Now put2 operator is left associative. So if you write std::cout <<a b, it is first std::cout <<a and the result <b. The expression in parentheses evaluates to std::cout, while the value of a is written on the standard output, and then we have std::cout <<b. So in effect, we get the values of a and b written on the screen. It is not necessary to write two statements. You can simply put them together as std::cout <<a b. So we can replace the last three statements in the above program with a single statement like this, and the values of I, D and C are printed. For the input, we have the std iStream class, and it has global object stdcin, which reads data from the standard input, which by default is the keyboard. Here is an example. stdcin greater than I. We have this greater than operator, which is the get from operator, and it gets input from the object cin. It gets the input from the first argument to the second argument, which is the integer variable I here. Here is an example. stdcin greater than I. This reads the character from the standard input to integer variable I, and next we read stdcin greater than str, and we print the values we have read. We compile and run this program. We have an integer 23, and the string we type is hello world. We print the values. The integer is 23, that's correct, but the string only has one word hello. The rest of the string is missing. We type the string as hello space world. Now space is a delimiter, and the system thinks that string is just hello because there's a delimiter between hello and world. We can correct this by using the getLine function, which reads a line, that is characters up to the new line. So we say getLine stdcin, str, which should read a line from the stdcin into the string str, and we comment the earlier stdcin greater than str, and we compile and run. Now there is another problem. I type in integer 23 and the program runs through. We don't get a chance to type in the string. The problem is that when I type 23, I also press enter, and integer I becomes 23, and there's a new line character in the buffer which comes to the getLine function. getLine sees the new line, thinks that it has got a string, and immediately returns. So there is no string nor a chance to enter one. This is not what we wanted. So what we should do, we need to skip the delimiter character new line after reading the integer I. So we say stdcin dot ignore 1000 new line character. This function discards characters till either 1000 characters are discarded, or end of file is reached, or the delimiter character, which is new line here, is found and discarded. With this, we discard the new line before the getLine function, and now the program works fine. In the previous examples, we have used put to and get from operators for built-in types like int and also strings. But we can use these operators for user-defined types also. Suppose we have a user-defined type struct student int roll number std string name, and we want to use the put to and get from operators with standard output and input like this. Int main student s while stdcin greater than s, stdcout less than s, less than stdendl, that is, read a student from standard input and write a student on standard output. And our format for student is like this: open brace, roll number, comma, student name in quotes, closing brace. And these are the operator overload functions for put to and get from operators. For these operators, we need a stream and a student structure, so there are references to these in the input parameters. Most important is that these overload functions return a reference to the relevant stream. This is how chaining becomes possible, because a reference to a stream is returned which is used for the next argument, if any. The output operator overload function simply writes the two data elements, roll number and the name, on the stream and enclosing the output in braces and putting a comma in between. The input operator overload function is somewhat involved because we need to do validation of input whether it is as per the format or not. If validation fails, std_ios base fail bit is set and the stream returns in a failed state and the main function loop terminates. Binary stream IO is important. In fact, very important because there are lots of times you create or modify binary files. These files are mostly for use by the computers. For example, a binary data file recording student data, image files like PNG, JPEG, document files like PDF, etc. So let's look at binary file IO in C++. And here we need to use the fstream header file for library classes. For file handling, there are three core file stream classes. ifstream for input file stream. This is for input operations and is for reading data from files. ofstream for output file stream. This is for output operations, that is for creating and writing data to files. And then there is fstream, that is file stream. This is for input-output operations. You can create, read and write data to files. Here is an example program to copy a source file to destination. We include the header files iostream, fstream and string. Here we will copy source file to destination, so we need the source and destination file names. We get the source and destination file names from the standard input stream CIN with string variables source and dest. Next we open the two streams. The first input stream ifstream is for the input stream and os for the output stream. The flag std_ios binary specifies that it is a binary stream. Data would be written or read exactly as it is with absolutely no translations like LF to CRLF. If both IS and OS are valid streams, then let's look at the important line OS less than IS RDBuff. Each stream is associated with a stream buffer. The data in a stream flows through a buffer. It is like file to stream buffer to the program. A stream buffer is a low-level implementation detail. IS RDBuff gives the pointer to the stream buffer. The put_to operator transfers the data to the OS stream. A string is a sequence of characters. For example, hello world is a string. In C programming, a string is implemented as an array of characters terminated with a null character so that you know where the string is terminated. As all C programs are also C++ programs, the C style strings are available in C++ also. But in C style strings, you need to worry about the memory, whether you are overshooting the space available, and also whether the terminating null character is in place or not. The good news is that the standard library in C++ provides strings where you need not worry about the memory management for strings or whether there is a null character there or not. In C++ strings, all this is taken care of automatically. You need to include the string header file to use C++ strings. For example, here we have the string ABCD1234, which we can print on the standard output. A string of std string class can grow or shrink during the runtime. The underlying memory management for creation of a string and increase in its size at runtime is automatic. Operators. The subscript operator, which is the square brackets, gives the character at that index. We can treat the string as a character array. A string starts at 0 index and the last character is at string length -1. Equal to is the assignment operator for assigning a string value to a string object. Plus is for concatenation of two strings. Plus equal to is add to string or append string at the end. Here is an example of operators for strings. First we create three string objects str, str1 and str2 with initialization, and then we have C-style string comma which contains a comma and a space. So str has value high to start with. Str is assigned str1, so str is now hello. We append comma to it and it becomes hello comma space. So we can use C++ std string along with C-style strings in expressions, and then we append str2 to str, it becomes hello world, and finally we append exclamation mark to str and it is the final string hello comma space world exclamation mark. If there are string literals adjacent to one another, these are concatenated into a single string by the compiler. For example, if we have three string literals hello, comma and world, the compiler makes it a single string hello world, and here in this case it is printed. Since std string is a class, it has got member functions and we'll look at some of them. The length function gives the length of the string. For example, std string str initialized to Shanks pony, and we can print its length, which is std cout str.length std endl, and this prints 12. Now accessing the individual characters of the string, we can treat the string as an array. Suppose we have a string std string str initialized to silver bullet, and then char a equal to str0, char b equal to str.length -1, and if we say std cout a comma space b std endl, and this prints the first and the last characters of the string, which are s and t. The substring function substr returns a copy of the substring inside the given string. The parameters are the index of the start of substring and the length of the substring. For example, we have the string str initialized to good, bad and ugly, so substring at 6.3, that is start index is 6 and length is 3, is bad. And with the replace function we can replace substring. Suppose you want to replace the substring bad in str with excellent, we can say str.replace 6.3 excellent. So three character substring bad are replaced with excellent, and replacement is in situ, that is replacement string can be smaller, equal to or larger than the original substring. The relational operators are equal to, not equal to, greater than, less than, greater than equal to, and less than equal to. And these relational operators can be used in expressions involving strings. For example, std string s1 initialized to effect and std string s2 initialized to effect. So the expression s1 greater than s2 evaluates to false, and the expression s2 greater than s1 evaluates to true. And if we have expression s2 equal to effect, which indeed it is, the result is true. The standard template library STL was developed separately in the 1980s. It was the work of many people, most notably Alexander Stepanov, David Musser, and Mang Lee. The work of STL was considered highly, and in the 1990s, efforts were put in to include it in the C++ standard. Consequently, the STL became a part of C++ in the C++ 98 standard. The classes of STL are available under the std namespace. The important part of STL is its unified design, and the parts of STL work in a similar way and they work well together. There are three major concepts in STL, and these are containers, iterators, and algorithms. Together, these three are called the STL triad. Containers provide storage for elements. Algorithms provide the logic for getting the work done using the elements in the containers. Iterators provide the algorithms a standardized interface to the elements of the containers. And the main thing is that they all work together. We look at containers, algorithms, and iterators in this video. A container is a class template. Its main objective is to hold objects of a type. The objects are called the elements of the container. A container manages memory for its elements and provides interface to access, add, modify, remove, and iterate over the elements. The standard template library provides a host of containers, so we can use them straight away in our programs as they are highly optimized. And some of the important containers provided by the STL are vector t, it's a variable size vector; list t, a doubly linked list; forward list t, a singly linked list; dec t, a double-ended queue; set t, a collection of unique keys ordered by their values; multiset t, a set allowing duplicate keys; map kv, an associative array mapping a key into value. So it has two type parameters, k for key and v for value. Multimap kv, similar to map but allowing duplicate keys. Unordered map kv, it's a map using a hashed lookup table. Unordered multimap kv, a multimap using a hashed lookup table. Unordered set t, a set using a hashed lookup table. And unordered multiset t, a multiset using a hashed lookup table. Of these, we'll look at vector, list, map, and unordered map containers in a little detail. Vector is a container class template. It contains objects of a type. These objects are the elements of the vector. A vector is like an array. Its elements occupy contiguous successive memory locations. We can do random access of elements using the subscript starting with 0, and the last element has the subscript vector size -1. The number of elements in a vector is its size. The number of elements can increase or decrease at runtime. So a vector appears like a dynamic array. Its size can increase or decrease at runtime. And this is how it looks like. Elements and SZ are kind of private data members. The vector appears like a dynamic array with subscript operator and also member functions. Here is an example program for vector. Student is a struct having roll number and name, and these are the operator overload functions for put to output operator and also get from input operator. In the main function, we have the vector student register, which is a vector of a student, and this vector has three student elements: John Doe, Joe Blocks, and Fred Nurk. We have the print register function where we pass a reference to the student register vector, and print register function iterates over the elements of the vector and prints each student. We can compile and run this program and it works fine. And now the member functions. The size function gives the number of elements in the vector. In the previous vector example, we can print the size of student register vector and it prints 3. The pushback member function adds an element at the end of the vector and the size of vector increases by 1. For example, we can say student register dot pushback 12359 John Smith, and John Smith is added to the student register vector at the end and its size becomes 4. The pushback function illustrates the expandability of the vector at runtime. The capacity of a vector is the number of elements it can hold in the currently allocated buffer. So essentially, size is less than or equal to capacity for a vector. We can print the capacity of vector with the capacity member function. Like here, we first print the size and the capacity. It prints the size of student register vector as 4, whereas the capacity of student register is 6. So if we add 2 elements to the vector, the size and capacity both becomes 6. And what happens when we try to add the 7th element? We can try that, and when we add the 7th element, the vector size becomes 7 and its capacity becomes 12. The capacity is implementation dependent. All we are interested here is when the size and capacity become equal and we add an element, the capacity increases. When the size of a vector is equal to its capacity and a new element is to be added, a new buffer for the vector is allocated dynamically. The existing elements of the vector are copied or moved, if possible, to the newly acquired buffer, and it becomes the memory buffer for the vector. The old buffer is deleted, and all this is done automatically under the hood, and to the user, the vector appears to be growing as new elements are added. Most of the time, we have some idea about the size of the vector, so we make a sort of guesstimate and say we might need that many elements at runtime, and we can avoid the overhead of repeated dynamic memory allocations as a vector grows. We can reserve memory for that many elements right up front. For example, we might think that the student register might have a maximum of 100 students, so we reserve space for 100 elements right at the beginning, and we can keep on adding elements to the student register vector. The vector size increases, but the capacity at the beginning was 100 and it stays that way till 100 students are added. If you want to add the 101st student, there would be dynamic memory allocation for larger buffer, and behind the scene housekeeping would be done so that the student register vector can have 101 students. The subscript operator is used for accessing the elements using an index in the range 0 to size -1, but by default there is no range checking of the index. So if the index is outside the valid range, the program may give erroneous output or it might crash. The @member function checks whether the index is within the valid range or not. If it is in the valid range, it returns a reference to the element at the specified position. You can read and modify it. But if the index is out of range, it throws STD out of range exception, which can be caught by the program. So here in this example, let's look at the for loop. The size of student register vector is 4, so I would vary from 0 to 4 inclusive, but I equal to 4 is index out of range situation. So STD out of range exception is generated, which is caught by the program in the catch block, and we get this output. The first 4 lines are okay, but when the index value is 4, it says this is greater than or equal to size of the vector, which is 4, and this is out of range. So using the @member function instead of the subscript operator, we are able to catch this exception and program works properly. It does not show junk or it does not crash. If you wish to use the subscript operator and also have the checking for index out of range, you can derive class say vec from std vector and overload the subscript operator to use the @member function for accessing the vector elements. For example, here template type name T, class vec derives from std vector T, public using std vector T vector. This is the constructor inheritance, and what it means is that all constructors of std vector T become available in the derived class vec T. T reference operator subscript int I, and here we use the @member function for returning a reference to the element at index I. So it says return std vector T at I. And the same for constant objects. Constant T reference operator subscript int I constant return std vector T at I. That's it. We can use the vec class template, and we define vec student register vector container, and we add 4 elements using the pushback member function, and then we print the student register where we access using the subscript operator. And here deliberately we are trying to go past the last element of vector just to see whether the exception index out of range is generated and whether it is caught, and it works as expected. Using the vec T class template, which is derived from std vector T, we can use the subscript operator for accessing the vector elements and also have the check for index out of range exception. Some key facts about vector. Vector is the most commonly used container in C++. It provides constant time O1 random access to its elements. This is the most important part. The time required to access an element is independent of the number of elements in the vector. Addition of elements at the end using pushback has also O1 time complexity amortized, as resizing is done only occasionally. The elements of vector occupy successive memory locations. This leads to good cache performance by the CPU. Vector is slightly slow in adding and deleting elements in the middle where it has O(n) time complexity. Vector is the preferred container in C++. stdlist is a container class template. It keeps a sequence of elements or nodes in a doubly linked list. Each node has the forward and backward links, or in common parlance, the next and the previous links, apart from the data members. Most implementations keep a sentinel node after the last element. The sentinel node has the next and previous links, but it does not have any data members. There's a link from the last element to sentinel and vice versa. Similarly, there's a link from the sentinel to the first element and vice versa. This makes it a circular doubly linked list. In most implementations, the sentinel node is embedded in the list object. So the links to the first and the last element of the list are available in the list object itself. Now the sentinel and the links are implementation details which help us in understanding the list, but these details are not specified in the C++ standard. The standard is silent on the implementation, and the details are left to the C++ standard library implementers. We need to use the standard library as per the public library interface. So to a user or programmer, the list appears to be a sequence of elements which can be accessed sequentially, no random access, and if you have an iterator at a position in the list, elements can be added or deleted with O(n) time complexity at the place pointed by the iterator. This operation is very fast because there is no shuffling of elements before or after the insertion or deletion. Not like the vector where the rest of the elements need to be moved up or down. It is not like that. Here, in this example, we traverse a list. Struct student has 2 data members int roll number, and std string name. The operator overload functions for output, put to operator, and input get from operator. And the std list container has elements of type student. It has 3 elements, and we have a function print register for printing the contents of the student register list. It uses a range for loop to iterate over the contents of student register and then printing on the basis of student name. That is, given a student name, we search for that student in the list and print the details. So it's a loop, read a student name and execute the function print student details. And in the print student details, we traverse the list from the beginning to the end using a range for loop. For each element, we check the name. If it matches, we print that element and return. And there is an error message if no student is found. Similarly, we have a loop where the user can enter roll number and we have print student details 1, and this function goes through the list sequentially as before, and if there is a match, the element is printed. Earlier in the print student details, we had used the elements in the for loop, but here in print student detail 1, we are using an iterator S. S is an iterator with initial value student register.begin, which points to the first element, and we stop when the iterator is at student register.end, which points one past the last element. And here we print pointer S, that is the element pointed by S. Next, we try to insert elements in the list. Say initially the list has 3 elements. We define 3 students S1, S2 and S3, and we'll try to insert these records in the list. There is push front member function for adding an element at the start of list, and there is push back for adding at the end of list. So we say student register push front S1. Student S1 is now added to the front of the list, and we say student register dot push back S3 for adding S3 at the end of the list. Now list has 5 elements and we wish to add student S2 at element number 3. That is, we wish to make S2 the third element in the list. So first we go to the beginning of the list by defining an iterator IT and the assignment IT equal to student register.begin. Now IT points to the first element. Next we say std advance IT2. This advances it by 2 elements, and now IT points to the third element. Now it is at the proper place and we say student register.insert IT S2, which means insert S2 at the location pointed by IT, and S2 becomes the third element. And if we print the student register list now, it is like this. We have added Jack Dawkins at number 1, Jane Doe at number 3, and Alfred Doolittle at the end. The splice member function in std list is for transferring a part of one list to another, or we can transfer one part of a list to another position in the same list. And here we use iterators for pointing the elements for transfer or for the destination location of the transferred elements. The main point is the splice operation is very fast, O1 time complexity. There is no copying of elements, only the pointer links are adjusted. As an example, here we have 2 lists, student register with 6 students and new students with 5 students. We wish to transfer 3 students, second, third and fourth in the new students list to the student register at the third place. First, we set an iterator in the target list. IT is the iterator which is equal to student register.begin. It points to the first element in the student register. We advance it by 2, that is std advance it2. So now it points to the third student. Now we go to the source list. Here we did two iterators, start and end iterators. it1 is the start iterator. it1 equal to new students dot begin. it1 points to the first element in the new students. std advance it1 1. Advance it1 by 1, so it points at the second location. Next, auto it2 std next it1 3. Since it1 points to the location number 2, it2 points to location 5. Next, student register.splice it new student it1 it2. Transfer new students it1 to it2 but not including it2 to location pointed by it. And we run it. The 3 students are not there in the new students list and they are there in the student register at location 3. The next job is to transfer students 6, 7, 8 in student register to position 2. Also in the student register, that means Jane Doe, Joe Blocks and Fednark should go up just behind Jack Dawkins. And we use 3 iterators. First, it points to position 2, the target position. it1 points to 6th location, Jane Doe, and it2 points to 3 locations away from it1, that is the 9th position, one after Fred Nurk. And we say student register dot splice it student register it1 it2. We can run the program and Jane Doe, Joe Blocks and Fred Nurk are transferred starting at the second position. And finally we can transfer what is left in the new student list to the end of the student register, and we need to say student register dot splice student register dot end new students. And Max Musterman and Hubbard Pocket have been transferred to student register and new students is now empty. So what is our take on list? In list we have the splice operation, which is very efficient. There is the merge operation where 2 sorted lists are merged into a single sorted list, and merge is also very efficient. The efficiency comes from the fact that the elements are not copied during these operations, only the links are updated. Splice is useful in implementation of caches and task schedulers. The list is useful when there are going to be a lot of additions or deletions of elements in the middle. What goes against list is that its elements are not contiguous. The elements are scattered in memory and there is pointer chasing coming into play at runtime. So cache performance may not be good. So vector continues to be the preferred container. The next container is map. Map is an associative container. Associative containers retrieve elements using lookup keys rather than sequential indices. Each element in the map is a key value pair. That is, a value corresponds to a key. The key is unique for each element in a map. Maps are implemented in C++ using red-black trees, which are self-balancing binary search trees. The time complexity for search, insert, and delete operations is O log n. A map stores key value pairs. Since map is a class template, it has at least 2 template parameters, something like std:\map key, t. So here we have 2 template parameters. Key is the type of the key and t is the type for the mapped value. Internally, map stores elements as key value pairs, that is std:\pair constant key, t. The constant keyword signifies that the key is constant. It cannot be changed after insertion. Only the value corresponding to the key can be changed. A constant key is required to maintain the internal integrity of the map's data structure. For example, here we have the map student register. The template parameters are int and std string. That is, the key is of type int, which maps to a value which is student's name and is of type std string. The print register function prints all the elements of the map. In a map, all elements are arranged in the increasing order of the key. Map elements are stored as std pair, which has two public data members, first and second. So we use a range for loop in which x iterates over the elements of the map and prints the first and second data members of each element. Next, since map is an associative array, we can index it using a key to get to the corresponding value. So we can say student register subscript 1, 2, 3, 4, 5, 7 and it prints Joe blocks. What happens if we use the subscript operator for a non-existent key? Suppose we say student register 1, 2, 3, 4, 5, 9 and there is no student in the map with this key. It turns out if the subscript operator is used with a non-existent key, map creates a new element for that key and fills the value fields with defaults. So here an element with the key 1, 2, 3, 4, 5, 9 is created with name as null and str is printed with nothing for the null value. This might be okay in some cases, but it is a kind of spurious record in lot of other cases and we might not want this. So in those cases, we don't use the subscript operator for accessing the element's value. We use maps find member function with a key value and it returns an iterator pointing to the relevant element. If there is no element for the given key, the iterator points to the end, which is the last element plus 1, and then we can conclude the element does not exist. There are many ways to insert elements in a map. We'll look at two of them. The first is the insert member function in maps. If the key of the given element does not exist in map, the insert member function inserts the element in the map. But if the key exists, nothing is done. There is no overwriting of data existing in the map. The second way is to use the assignment operator. We can index a map with a key and assign a value. After that, this element is part of the map. If it did not exist earlier, a new element is created. If it existed, the existing value is overwritten. For example, there is an existing element 1, 2, 3, 4, 5, 6 John Doe. Now if we say student register dot insert 1, 2, 3, 4, 5, 6 Alice Wonderland, nothing happens because there is an existing element 1, 2, 3, 4, 5, 6 John Doe. But if we index the map using the key and make the assignment student register subscript 1, 2, 3, 4, 5, 6 equal to Alice Wonderland, it overrides the value John Doe with Alice Wonderland. Now looking at example for creation of map elements, student register dot insert 1, 2, 3, 4, 5, 9 Hubbard Pocket creates an element with key 1, 2, 3, 4, 5, 9 and value Hubbard Pocket. Similarly, using assignment, if we say student register subscript 1, 2, 3, 4, 6, 0 equal to Sarah Pocket, the element 1, 2, 3, 4, 6 T Sarah Pocket is created. We can erase elements from a map, and the simplest way to do that is to erase using the key. If there is no element for the given key, nothing happens. Alternately, we can erase an element using an iterator. However, it must be a valid iterator and it must not be the end iterator. You can erase multiple elements, an iterator range, IT1 to IT2, and here also IT1 and IT2 must be valid iterators for the map, and IT2 must be greater than or equal to IT1. And to erase all elements in a map, we can use the clear member function. For example, when we say student register.erase 1, 2, 3, 4, 5, 6, then the element 1, 2, 3, 4, 5, 6 is erased. Now erasing using an iterator, we initialize the iterator with find function for the key 1, 2, 3, 4, 5, 8 and check that iterator is valid, that it is not the end iterator, and then we can say student register.erase it and the element is erased. So the clear difference, in case of erasing by key, it is not necessary to check whether the key exists or not, but for the iterator we need to check its validity. In fact, when we say student register.erase 1 and there is no element with the key 1, nothing happens. Now we can erase elements for an iterator range. So for that we add 2 elements in our map, making a total of 5 elements, and now we wish to erase elements 2 to 4, and for that the map must have at least 4 elements. We set IT1 iterator to begin and then we advance it by 1, so IT1 points to the second element. Since we wish to erase 3 elements, we make IT2 point to 3 elements after IT1, and then we say student register erase IT1, IT2. Now using the iterator range, both IT1 and IT2 must be valid iterators and IT2 must be greater than or equal to IT1. These are the requirements for using iterator range in the erase function. And we wish to erase the entire map, we say student register.clear and all elements in the map are erased. To summarize on maps, we can say map is an associative container. It contains key value pairs as elements. The elements are ordered in the ascending order of the key by default. It provides O log n time complexity for lookup, insertion, removal of elements. Regarding the cons, the memory used by maps is not contiguous, so there is poor cache locality. The memory overhead is high and it involves pointer chasing. Maps are fast, but unordered maps, which we will see next, are faster. Now we look at unordered maps, which like maps is an associative container and stores key value pairs as elements. The implementation is quite different from maps. Unordered maps are implemented using hash tables. Now hash table is an all-encompassing concept. It comprises of data structures and algorithms. For data structures part, we have a bucket table, which is an array of buckets, and each bucket holds 0 or more elements. At the implementation level, a bucket can be a linked list of elements. Regarding algorithms, we have a hash function which transforms a key value into a hash value. HV equal to F key. F is the hash function which converts the key to an integer hash value. We can map the hash value HV into an index into the bucket table by say index equal to HV modulus n. This gives an index value in the range 0 to n-1. Now the problem is multiple key values can ultimately convert into the same index in the bucket table. This is called a collision where multiple key values convert to the same index. A bucket can have multiple elements in a linked list. This is a simplified way of putting things. The actual implementation might be more involved. A well-tuned, unordered map, that is, a bucket table of adequate size, a good hash function, and also a good mapping function which maps the hash value to a bucket table index. If these are well tuned, we can get O1 time complexity. However, the worst case scenario is ON time complexity. The member functions for operations in unordered maps are the same as that of maps, and we can easily convert the map program to the one that uses unordered maps. First, the header file. It should be unordered map. Then the type should be changed from map to unordered map, and we are good to go. We can compile and run the program. It produces the same results. The standard template library STL provides a triad of three fundamental interrelated concepts, and these are containers, iterators, and algorithms. Containers provide storage for their elements. Algorithms provide the logic for doing work on the elements of container, and iterators provide a standard interface to the elements of containers. Iterators are the link between algorithm and containers. Algorithms work on a sequence of elements. Sequence is represented as the elements between two iterators. Algorithms work on half-open sequences. A half-open sequence between A and B is specified as left square bracket A, comma B, right parenthesis. This means range between A and B, where A is included and all elements up to B are included, but B is not included. Algorithms do work like copy, sort, unique copy, etc. on the elements of the sequence. Algorithms are part of std namespace, and the header file algorithm needs to be included. Some of the algorithms available in the standard library are std find first last value. This is for searching value in the container. It returns iterator to the first occurrence of value in the range first last. Std find if first last f, where f is a predicate, and this returns an iterator to the first element for which the predicate f is true. Std count first last val. This returns a number of elements which are equal to val. And std count if first last p. Count if returns the number of elements in the range first last meeting the criteria indicated by the predicate p. Std replace first last old value new value. In the range first last, replace old value with new value. Std replace if first last p new value. In the range first last, if the predicate p is true, set element value to new val. Std copy first last out. Copy the elements in the range first last to the range starting at iterator out. There must be adequate number of existing elements at the destination range so that the source element can be copied. Std copy if first last out p. Copy the elements from the source range to the destination out if the predicate p is true. Unique copy first last out. Unique copy copies the elements in the range first last to the range starting at iterator out, and most importantly, removing consecutive duplicates. It copies the first element, the next element only if it is different from the previous, and so on. Std sort first last sorts element between the first and last iterator in ascending order, and std sort first last f. This sorts elements between the first and last iterators using f as the sort criteria. F is a custom comparison function. We can define f suitably to sort in a certain way, say descending order. Std equal range first last value. For this function, the range between the iterators first and last must be sorted. It returns results, which is a pair of values. Result.first is not less than the value, and result.second is greater than the value. And we have std merge first one, last one, first two, last two, result. Here first one, last one and first to last two are input sorted sequences and the result is the merged sequence. An iterator is a pointer-like object used for accessing elements of a container. We can dereference it just like a pointer and access the pointed element. There are two important iterators, begin and end. The iterator begin points to the first element in the container. The iterator end points to one past the last element of a container. The end iterator cannot be dereferenced. It is there just to tell that there are no more elements to be accessed. For example, here we have a vector v with 4 elements and we can access the elements using the iterator p. The type of iterator p is std : vector int : iterator. Normally we do not write all that, we can just say auto p and it works fine. So we start with p equal to v dot begin and that is the first element and the loop ends when p is equal to v dot end. Note that we never access p when it is equal to the end iterator. We just stop there and the loop terminates. There are library functions that return iterators based on certain criteria. For example, let's say we have a vector int v and we wish to find elements with the minimum and maximum values. So there is a library function std min-max element which gives iterators that point to the minimum and maximum values, and we can receive these iterators in an object of type std pair. Std pair is a structure with two members. Here we have std pair where each member is an iterator to a vector of int, or we can just say auto p and it works fine. But we can do better. Instead of saying auto p, we can say auto square brackets minute maxit, which is structured bindings. So because our assignment, minute becomes equal to the first element of pair and maxit becomes equal to the second element of std pair. Now minute and maxit are iterators and not values. What happens if the vector is empty? If the vector is empty, it has no elements, v dot begin is equal to v dot end, which is the last, and both minute and maxit would be equal to the last, and the dereference operator is not defined for the last. So if we do that, we get a runtime error like segmentation fault. We can put a small check if minute not equal to v end before the print statement, and it works fine for empty vectors as well. Stream iterators are iterators for input and output streams. Stream iterators help in using the STL algorithms with streams. C++ has the STL triad of containers, iterators, and algorithms which work together to provide efficient and reusable code. The containers are sequences of elements. We can use iterators for the elements which can be connected to algorithms. Now if we look closely, the data passing through a stream, it is also a sequence of some object like character, int, string, a user-defined type, etc. So if we have iterators that can get hold of this data sequence, we can connect that to STL algorithms and get the full benefit of STL algorithms for the data flowing through the streams. Thus, we have stream iterators, and these are std istream iterator t for formatted input of type t, std ostream iterator t for formatted output of type t, std istream buff iterator char for raw character input, and std ostream buff iterator char for raw character output. Since we are dealing with objects and not raw characters, we will confine our attention to the first two here in this video. std iStream iterator T is for formatted objects of type T in the stream. For example, std iStream iterator int ii std cin. This is an input stream iterator ii handling objects of type int and connected to the standard input std cin. We need a special sentinel input stream iterator for signaling the end of input, and it is std iStream iterator int eos braces. This indicates the end of input. There are no more objects of type int in the input stream. Similarly, we have output stream iterator std ostream iterator int oo std cout, \n, the new line character, which means oo is an output stream iterator connected to std cout, and it has a delimiter \n, the new line character. So this iterator adds a new line character after each integer object. Here we have a small example of using stream iterator. The vector v has three string elements a, b and c, and we have output stream iterator os connected to std cout, and it puts a space delimiter after each string. So there is the standard library copy algorithm to which we pass the iterator vBegin and vEnd and the output stream iterator os. It copies the elements of vector v from vBegin to vEnd to stream iterator os, and we can see the results. Another example, ii is the input stream iterator, eos is for signaling end of input stream, and oi is the output stream iterator. We create a vector v of std string for the range input iterator ii and end of stream eos. We sort the vector v, and vector v might have duplicates. Since it is sorted, the duplicates are arranged as consecutive elements, and we do a unique copy of vector from vBegin to vEnd to output stream iterator, and this is the result. The elements are sorted and duplicates removed. A predicate is a function that returns a Boolean value, false or true. Predicates test conditions like whether a given value is odd and return false or true. Or another example, check whether a given value is greater than a base value and return false or true. For example, we might wish to find the first odd number element in a vector of integers, and we can use the algorithm std find if vBegin, vEnd is odd. Is odd is the predicate. It checks whether an element is odd or not, and this is a program where is odd is a function object or functor. We can use a lambda expression instead of functor, and the code is like this. You can find the code for all the examples in this video at SoftPrayog website. Here is a QR code and the link is there in the description. If you like this video, please share it and subscribe to our channel. Thank you.